and if there are no any questions, comments so far, then plan for today's session is following. Hopefully we will finish theoretical part about networking, and then I also will explain you what you should do in next homework, which will be also about networking. In theoretical part we will have two main topics. One is web and other networking things after that. And before we go forward, what I wanted to show. Difference between internet and web, or the internet and the web, if you think that these particles are important. So internet is everything about internet protocol, and web is everything about HTTP protocol. And of course, when you do use abbreviations, you shouldn't say IP protocol, because P here and P here means protocol. So if somebody writes something like this means internet protocol, hypertext transfer protocol. So, and because web uses internet, so web is smaller part than internet if you look on definitions. But because web is so important part of everything around internet, of course many of humans, people, users, do not see much of difference. And then of course here for some user is Facebook. With Facebook, WhatsApp and what was third application, I don't remember. So Facebook of course uses internet protocol, it uses HTTP, and if every thing you see through the web, through the internet is just Facebook, then of course you may not see difference between these three. But some examples what you may not see how web is different from internet is, for example, FTP, file transfer protocol, not widely used anymore. SMTP, mail protocol, not widely used anymore because everybody uses mail through the web like Gmail or whatever. What else maybe is there? How it's like point to point, I don't remember, and some other protocols as well. But because web is so important part, so you don't see. And now, what is web? So, little bit about history, little bit about most important parts about web, key properties of this hypertext transfer protocol, and then a little bit about web infrastructure. So before web, nothing important is developed in empty vacuum, empty place. Before web, there was other idea how to organize information and how to make it reachable. And it was implemented by a project called Xanadu or Xanadu for Americans. And it was implemented in a way like shared folders for documents and specific text editor, which allowed you not only to see this but also to edit. So something like shared structured documents between servers with rich text format. And inside this rich text format there was so-called hyperlinks where you could refer to another document to another server using organized schema like this server, this folder of this server, this document, blah blah blah. And good thing about this approach was that if you had permission to change this file on the server, there was no difference between just reading text and writing text, so it also implemented early ideas of wiki systems that you not only read but also write. What was not so good that it was rich text document format like another format besides Microsoft Word, Microsoft Excel and etc. And it was too centralized because to get reference to these other documents, of course, you had to have permissions, and so it was quite hierarchical, but it was quite active around 1970s and 80s between different kind of computer scientists. But then physicist came in, and he also knew about this Xanadu project and didn't like it because it was too rigid, too structured, especially this rich text document format for these Xanadu documents. And so this physicist was Tim Berners-Lee, worked for CERN at that time, and he invented other approach which was much more crude, much simpler, and big difference was that in Xanadu project all hyperlinks were always checked in both directions. So if you created some hyperlink to other document and this document was moved, then this other Xanadu documents knew about incoming hyperlinks, and if some of this document was removed or whatever, they could message to other documents and fix them if you had permission control that this particular hyperlink should be removed because this document will not exist anymore. So modern content management systems do the same as Xanadu, but it's only inside one particular content management system. But Tim Berners-Lee decided that for practical purposes this is too rigid idea and too complicated, so he implemented a much simpler protocol, and most difference was that documents were not rich text documents but plain documents with some markdown syntax to change this particular style of text, and that when you refer to some document, this document doesn't actually know that some other document is referring to it, so you don't know about incoming hyperlinks, and so creation of hyperlinks become much easier. And so first implementation was created on Apple BEOS system, I think, which is Unix-like system like MacOS and iOS and different kind of Unixes and Linux system. But because it was not very popular system very early on beginnings, this system was converted and ported to Linux-based operating systems, and since then all web is mostly supported from server side on Linux-based operating systems. And so later, around year 1996, this protocol was established as Internet standard. In Internet standard there are documents called requests for proposals or requests for comments, or RFCs in short, and when there is nothing more to comment about some of these requests for comments, then it becomes adopted standard. And so on 1996 it was established as one part of Internet-based protocols, so it became international standard. And what is important here is that you may also have heard about HTML protocol, which describes this markup language for unformatted text documents, how to make it richer. But HTML standards have bigger range of evolution and of versions. Currently, all web browsers and web servers are using either HTTP 1.1 or 2 protocol or HTTP 2.0 protocol. And this is how this World Wide Web project looked initially. So not much of rich text, and only richness here is these hyperlinks where you can navigate from page to page, and everybody should know about this already. And so why this Xanadu project was unsuccessful and web was successful? And mostly it's because for web everyone had ability to self-publish, everyone could create his own web page in some hosting site. It was technically easy, it was independent from platforms, operating systems, etc. And also because at that time Internet protocol and features of Internet were much more mature than they were on Xanadu project, so Internet was much more global around that time than Xanadu. And so why Internet is always a little bit broken? Because important part of Internet protocol to web protocol is that you do not control both ends of hyperlinks. You control only outgoing hyperlinks to something else, but if your target changes, then of course you get broken link. And what are basic web principles? First, web is based on top of Internet protocol, or particularly TCP connections. That means controlled transmission of data from IP address to IP address, from port number to port number, using TCP connections. So that is Internet part of the web. And what is web part? First is URL, which means Universal Resource Locator, which shows how you can get different kind of resources, and URLs are globally unique. So DNS here is involved, and in terms of deal to organization, and then inside organization you can distinguish between resources using internal paths of these resources. Then you have different kind of requests you can send from browser to server, different kind of responses and response status. And so here request and responses is mostly text based. Browsers or clients send text request messages to the server, and servers send text messages back with additional information, and then you can also download other text-based and binary files, text-based files like cascaded style sheet, JavaScript, and binary files like pictures, sound, video, etc. And primary classical web do not remember things on server. So every time you need to remind to server something about you, like you are logged in and valid user into some web system, you need to send this information again and again and again to the server to remind these things. So memory is on client side, not on server side. If you go into more tricky details, then of course more modern web servers remember some things about sessions using these sessions data. So first important part is resource management of the web, and you do it using these strings of addresses. An URL consists of uniform resource locator, or URI. URI consists of unified resource locator and unified resource name. So URL part talks about protocol and about organizations in global scale, and then particular name is other part, more deeper, which is inside particular organization, inside particular web server. And what is important, first it starts with type of protocol, how you send data using TCP connections. Usually it's either HTTP or HTTPS, and modern browsers do not show this part, similarly as modern file managers do not show extensions of files. And I think it is wrong, because it hides quite important information. Then there are DNS name, and in general this URI is big endian system, so more important and more aggregated parts are on the left, and less important, more smaller parts are on the right. But of course DNS is little endian system, because bigger parts for DNS name or domain name are on the right and smaller parts are on the left. Then you may show port number, you may not show. For example, for HTTP protocol you may skip it, that it's port number 80, and HTTPS it ports number 443, and then slash and everything inside the server. And what is important here are two parts, that in this URI you can instruct either server side or client side. For server side you say key equals value, and if you have many you add ampersands or rounds. Then these are additional instructions for server. But then you can similarly have key equals value or something else after hash, which is instruction for client side or for web browser. So if you add something here, server does something. If you add something here, browser does something. So, and then you use HTTP protocol as a management protocol to handle this data, and it is text oriented as most of internet standards, because text is much easier to debug and handle, even if you send binary data, especially for older versions of HTTP. For example, images were encoded in base 64 encoding, which is binary data encoded into text. And then when client sends some message to the server, server does something with this information, and it responds and it sends some textual data back. Not everything is shown in web browser, but if you go into debug mode, you can see that there are some kind of related information about server, and one important part is status of request. Everything which starts with 1 means continue, everything which starts with 2 is OK, everything which starts with 3 is redirection. That server sends instruction to the client, please now open different resource with different URI. And everything starts with 400 is client error, something like client tried to open non-existing resource or no permission to get this particular resource. And everything starts with 500 is server error. For example, server is busy or something like this. And by the way, these are reused numbers. Similar numbering system is used for email, status, and for some other applications as well. And when server sends response, in some cases it may respond only with so-called metadata. For example, you do not get the actual HTML content back, but you will just get so-called response headers, for example, to say that data are not changed. And this is quite frequently used for speed improvements. For example, when we talk about caching, some of parts of web might not actually be requested from the internet or web because nothing has changed so far. And then everything here is so-called resource metadata, which are sent from client to the server. How does it look like? So if you know HTTP, then you can work with HTTP protocol even without web browser. You can just write messages, and to write text-oriented message to the server, you may use application called Telnet. And because Telnet was originally used for a remote connection, like nowadays SSH is used, but today Telnet is not used anymore because it doesn't have any encryption between client and server. So if you manage your remote server with Telnet, then every interaction with your server can be read as open book if you, of course, understand the Telnet protocol. And so I connect to this server, and I think original port number for Telnet was 20, but because I want to talk with web server, not Telnet server, I say that port number will be number 80, and then I write something like get root folder using HTTP protocol, let's say 1.1, and then on send. And here I got response back from the server, and what it says here, it sends some metadata, these response headers, that it also uses HTTP 1.1, response status is 400 or bad request, and some information about server, what is time, what is server, what is content length, connection is closed, what is content type, and here is HTML sent to me. So what went wrong here? When we'll talk about at the end about so-called virtual hosts, there are servers where on one IP address you may host several websites. And in this particular server, there are several websites on the same IP address, and therefore I need to say host name. Okay, maybe I will. it was in different order. Okay, I need to search my notes. Yeah, so now it works. So where is difference? Difference is precise instructions to the server. So because this server hosts several websites on the same IP address, important part is, I had to say this host after get, that I refer to the website test.odo.lv, and then it sends some metadata here, and here it responds with HTML, just it works. And if we want to do something different, so look here that I'm still connecting to server with domain name test.odo.lv, but here I'm saying please show me relevant content for website with domain name odo.lv, and then I got different response here, move it permanently, because HTTPS protocol should be used here instead of plain HTTP, and you can emulate HTTPS protocol as well if you are curious. Only difference it is more complicated, something like this. And then I got some response. There's HTML. Because I'm searching for and now I got very long HTML back here. So that's about this interaction, and what is important that in general protocol is stateless. Servers do not remember anything. In general they may remember, but it's not required. And what is good thing is that you can create many concurrent parallel servers sharing the same IP address, and it will scale up pretty well because servers don't need to remember anything. What is not so bad that it's duty of the client or web browser to remind the server about the state. For example, I'm valid user, so that is bad. But so how this state is handled? It's handled with so-called cookies, and one of instructions what a server may send you is set cookie, and somewhere here before HTML we see this response here. So this is instruction to the web browser that every time if this browser should remind to the server that it is the same browser accessing this server, it needs to send all these additional cookies here, what it got from the server. And in this particular case, it is more complicated web server. It actually remembers things about users. So only thing you need to remember is session ID, which is just pseudo-random generated number. But because of security reasons, client needs to remind some other things as well. So server might send different kind of cookies as these kind of text instructions, remember this, remember that. And then every time when new requests are sent to the server, all these values of cookies also need to be sent to the server to remind the server that this is still the same user working in the same session to the server. And HTTP standard allows to use basic HTTP authentication, and it is again simple variant of base64 encoded concatenation of username, colon, and the password. And if you do such authentication inside encrypted HTTP protocols, then of course everybody can read your passwords and usernames as open book. And this is again one of the reasons why HTTPS protocol is used mostly. And then if some client tries to open some resources which are not allowed to this particular user, then of course you get error message back, and again you need to remind to the server that you are this particular user for every request. And then most widely today is used HTTPS protocol instead of HTTP protocol. And where is difference is following, that before starting sending these letters here, like this letter from client and this letter from server, you establish encrypted channel where public key cryptography is used. We will talk in details about this later. And this allows to establish encrypted connection first. So here, when I emulated HTTPS protocol on my terminal, what I did is I connected to the server. Server sent its public key inside this certificate, and then this public key is used to encrypt sessions to the server. And when client sends back any information, only server may actually decrypt it using its private key. And so HTTPS means HTTP over Secure Socket Layer Protocol. Initially, this protocol was abbreviated with TLS, or Transport Layer Security, but for different reasons, few years ago they decided that a better abbreviation and name for this protocol is SSL, not TLS. Old school web engineers still are talking about TLS, not SSL. And the TLS version 1.0 is the same as SSL version 3.0. It may add some confusion, and actually both of these variants of protocol have no known weaknesses. So you actually should use TLS 1.2, which is SSL 3.2. And then I think everybody of you should know basic principles about HTML, how it is sent back. So it is plain text, where everything for not plain text is described using these marks: smaller than, name of tag, there may be some key equals value parameters for it, and then closing tag. And then this HTML is interpreted by web browser, and it may also, while it's interpreting, may request more resources from the server with different URLs. And history of HTML. So initial widely used HTML version was version 2. And now most of web servers are using HTML version 4 or HTML version 5. HTML version 4, what is important about this is that it is compatible with XML format, which is more strict and more machine readable format. But HTML5 again is with more relaxed rules about these elements and tags what you can use. So, and it also has better support for cascaded style sheets and standardized JavaScript API and improved media support, etc. So, particularly for web server I'm using, it still says that it is sending response back in HTML version 4 point something, but if I include some new elements coming from HTML version 5, in most of cases browsers still understand it. So even though it's not proper according to the standard, in most of cases it works. And then servers may send instructions for web browser to download many other files which are not part of initial request. These are bunch of CSS files, bunch of JavaScript files, images, audio, video files, etc. And okay, we can do some demonstration. How does it look from the client perspective? From client perspective, it looks following: that we open some web browser, and we can open debug mode for it, and so here we see how this interaction worked between web browser and server. So first, web browser sent following request headers to the server, and you see that browser sent more than I did in my telnet session. And what is important here is this host.test.lv, because without that it will say some kind of error here, because web server cannot distinguish what kind of content it should send back here. And then server send different kind of things here back. And these response headers are textual information key column value from the server side. And you see here that now cookies are set because it's simple website which shows that it works. And if we open some wrong place, we got here response not found because there's no such URL on this web server. But if we open something more complicated, so here we see that the timeline is much more complicated. Initially, browser sent these request headers to the server, and server send these response headers, also including some of instructions about set cookies. And when I refresh this page, now when this browser got this cookie, it reminds that it is still the same the same session, the same browser, resending this value of cookies again and again and again. So, for example, look here on this end here, we resend it. Can I make it longer? I look at it on here. So, and for example, if I log into this system, let's refresh home page again. Then you see that username is sent in some kind of encoded format, some validation key, password. So every time I want to remind to the server that this is valid user logged into system, all this information should be resent to the server again. I went somewhere wrong. So, and that's how it works. There are clients sending requests to the server or these web browsers, servers responding to them, and then there may be some intermediate parties in between, like proxies, which provides different kind of extra functionality. And here is, for example, if you want to know about history of different kind of web browsers, one of early browsers are these where, for example, Mozilla, and somewhere here is Firefox, somewhere here is Opera, and somewhere here is Lifeline for Internet Explorer and Microsoft Edge. So they are quite a lot. And so web servers are handling these requests coming from client. They send data, and when these data are interpreted by the client, then these clients requests much more different kind of resources. So here is CSS files downloaded additionally. Here are list of JavaScript files downloaded additionally. Here is list of pictures downloaded. No other multimedia here, but if we open, for example, some page with multimedia, then you see, for example, and not everything is downloaded here. Initially you see that only few kilobytes were sent there. And then there may be many websites on the same web server, and in particularly for this web server there are two websites hosted on the same server with domain and website name odo.lv and with domain and website name test.odo.lv. And so if you host multiple sites per machine, then one of important parts is that you how to say to which particular host you refer to. For example, here we can always connect to just odo.lv. Actually, we can use its IP address. port number 80. And you see that in this case it says you don't have permission to access this resource. Why? Because there is no default website put on this server, so the default website is just this error page. But if you say get then you get this content, it works. And if you say open homepage, then you get response that it should be opened to HTTPS protocol, and on web browser it looks following. You try to open website odoo.lv, and you see that if I would press stop here initially, how can I stop it? No idea. Then I would see this response as here in Telnet here on small time. This web page moved permanently, the document has moved blah blah blah, and then this is instruction to the web browser. 3.1 moved permanently, it means browser needs to open different URL, so it opens automatically different address and then does everything here what is required starting from there. And similarly, there may be many servers using the same domain name or website address like odoo.lv, but there may be many physical servers because of load balancing. For example, for large companies, there may be even large farms of servers, all servers handling requests to the same website. And sometimes it makes problems. For example, you open your internet bank, you work on it, and then suddenly you lose session, so you are logged out of this system. What usually is happening there is that your requests from this load balancer were sent to different server who do not know anything about your particular values of cookie, about your particular session, and so this session is lost. And so in general, this interaction between client and server is going request item, transfer item, back request item, and of course if you need to download like 33 different resources, or if you open something like large news portal, then if you do it sequentially, it takes quite a lot of time. And how can you improve it? You improve it in following way, that as soon as client knows that it needs to request many resources, it requires to request many resources at once. And then, when server is ready, it responds with many responses back. And so it makes things faster. That was strange. And here you see that when I open this website initially, quite a lot of resources need to be downloaded because these are large and websites with quite a lot of content, and so you see it's still downloading. But if you will look here on Lifeline, you can't see very nicely here, you will see that there are actually many requests requested for these resources at once to make it more parallel. So, and about these persistent connections, other thing, how can you also make it faster, and it's used in more advanced way for HTTP protocol 2.0 or more, is that you can request even more requests at the same time. And so this is how it's working when you do not have advertisement filters and you open some large web portal at first time. And so, because many things may go very slowly in web, and servers in general tend not to remember anything, you use so-called caching. And what is caching? Caching means creation of local copy. And caching may be happening on different places. And first thing where it may be happening is inside web browser. For example, I open this website on second time, and I see here that quite a lot of resources were actually not downloaded anymore. We could see this. Somewhere in this data there should be send that usually what a web browser sends is so-called head request, which means just say is this resource changed or not, and you got small response like no changes. Then this large JavaScript or whatever is actually not downloaded. Where I could here. It doesn't show what is cached here. So, but what I wanted to, and it's not deactivated, to show that first caching level happens in web browser is that the web browser itself creates local copy of this data, and if in server response it says that it expires, for example, somewhere on year October 2022, then browser actually do not try to request for these particular resources like JavaScript files which are not changing frequently till to October 2022. Or if you clean up your cache, like press Ctrl Shift Delete, and you clean up your cookies, cached data, etc. So that's one thing what the browsers do. And for example, if you check how large your cache is, what I wanted to show. That. So it's mostly local cache, and this is for this virtual computer, for my physical computer. In local hash, it has stored almost 500 megabytes of data. But then if you work in large organization, then there still may be that quite a lot of additional resources are requested from different user computers, which is mostly the same. Then these organizations may introduce proxy servers. Proxy in Latvian is starpnieks serveris, which work in between these individual web browsers and actual internet. And they work in the same way. So they check, for example, what is validity time for particular resources. And if some of these users require the same resource what was already requested a few minutes ago, and it is valid, for example, for hour or whatever, instead of sending this data from actual web through the internet, it sends to these browsers local cached copy of this data. And it works very nicely without encryption, or for plain HTTP protocol. It becomes much more complicated if you use HTTPS protocol, because HTTPS protocol actually means end-to-end encryption. Everything between, for example, this web browser and this server is encrypted. So proxy servers actually, in general, do not understand what you are requesting and what are these requests required, because remember, these requests required are just text messages sent to the server when this TCP/IP connection is already established, and if it's encrypted, so these proxy servers do not know anything. And what do? Usually they work in the following way, that if you use HTTPS protocol, then everything is encrypted from the client to the server, and proxy server just see encrypted data sent from this IP address to that IP address to this port number to that port number, but it doesn't know what exactly was requested and what is responded. So in large organizations, what they do is following, that you create one encrypted HTTPS session to the proxy server, and then of course everybody in between this client and this proxy server just see encrypted data, and then this proxy server creates another HTTPS session between this remote server and this proxy server, and this becomes much more complicated. And because it's quite complicated, in general you use proxy servers for HTTPS protocol only for very large organization, when this additional complexity actually is worth doing it. But in general, if you create some kind of proxy server on your home router, if it allows you to cache some data, it creates cache only for unencrypted HTTP protocol, which is minority today in most of networks. So on this, if these proxy servers are close to the clients, are called forward proxies, but there are also reverse proxies which are close to the server, and they work in the same way. So here is some complicated and quite slow server with content management system for banking or enterprise management or whatever. And if everything is given directly to the server, it works, let's say, 10 times slower than if everything is prepared. So then these large organizations may create so-called reverse proxies, which does the same. If the server needs to provide some web page for Microsoft, Oracle, Google or Facebook, where content do not change frequently, these prepared copies may be saved on these reverse proxies, and until these documents are still not outdated, they are relevant. Instead of creating everything in this content from scratch or dynamically, they provide already prepared copies for these clients. And again, if it's HTTP protocol, doing this is very easy. If it's HTTPS protocol, what is actually happening is that these clients are creating HTTPS session or encrypted between this reverse proxy server and this browser, but between proxy server and that server, usually it's actually not encrypted session at all. It is simple plain HTTP protocol. And actually something similar works on my website. For example, there is no encryption between reverse because I'm using a Java application which listens on port number 8080. For example, I showed you how it looks from external side, but if I connect to this server, I can say telnet and I got response here from this application server, and as you see it's neither port number 80, neither port 443, but it's this. And actually I needed to say something like get xwiki. And then it got something wrong here. Something like this. So this encryption in my website is not coming internally here, but encrypted data with HTTPS protocol is only between client and this reverse proxy. And reverse proxies are quite widely used for any larger web system. And then for insanely large companies, there may be using external service called content delivery networks. What are content delivery networks? These are large proxy server farms in entire world. And for example, if you are a company like Google or Facebook or Amazon or I don't know, Microsoft, then you have your main servers somewhere in the USA, but requests to these main servers from entire world to the main server, even with these reverse proxies somewhere in the USA, is still quite a long shot somewhere here from Latvia or Russia or China. And what they can do is, of course, they may create data centers like Google around the entire world. Something in Europe, something in USA, something in Asia, in Micronesia, South America or whatever. But you may also require so-called service from these content delivery networks, which work like proxy servers for your company, and these proxy servers are around the entire world, and they create also fake or another entries when you open like Microsoft.com. Not actual IP address are sent to Microsoft or Google servers, but you open some other IP address which belongs to these CDN networks. And there are quite a lot of companies now which allows you to do this distributed networking, content delivery network, and therefore it may be happening that if something goes wrong somewhere in the Facebook or Microsoft, you see something like Cloudflare company or Akamai. So what they are doing, they are creating local copies of some of content of these websites, and instead of opening these original web servers, you are actually opening something else. And again, if you are using HTTPS protocol, then of course they cannot just present transmitted data which are encrypted with HTTPS between actual Amazon or Microsoft server and your computer. But what you are actually doing, you create HTTPS connection between these content delivery networks and your website. And good thing is that, for example, if you require such a service, and for example, if you are hosting your server in Cloudflare, infrastructure they provide it included in standard cost. So they actually provide HTTPS protocol for your website as well, because this HTTPS protocol and this certificate as a public key for server is actually not needed on your website, but it's needed here on these content delivery network services which are provided by these companies. And then what do? They can work in two different modes. In most of cases they work in pull mode. Every time client requests some particular page of this website, they create local copy and store it for some time. But if you are preparing for some large campaign, like for elections or whatever, you actually can pre-store these copies of these content delivery networks in advance, so that when clients will be opening this web page, they will be opening web page and get content from many distributed servers inside these content delivery networks. So, and most popular companies are, I think, Akamai and Cloudflare, but there are other companies which provides this as well. And so then it works in such way that you may have different kind of local data centers somewhere in Europe, in Asia, whatever, for this website, and then when clients open this, you actually do not disturb your main servers, but you deliver this content from more local servers closer to these clients. So that's about these things, and that is about web. Any questions or comments so far? Do we create some break now before we go to another topic? So let's make some break. I do not know exactly about this error. Full sequence of events should be described to understand, but I think this program is not wrong. You are trying to open some file which is not tar archive. So let's make a break. And then we will continue. That is still wrong. It will be something like I like this. So, a little bit more how actually internet works and some other networks where internet protocol is actually not used. So, in previous lecture I already told you there is difference between hubs, switches, bridges and routers. But when we deal about data transmission from place to place, what is important here is that in most of cases we are using Ethernet network as a basis for wired network and some kind of Wi-Fi for non-wired network, but from theoretical perspective they are quite similar. I will tell you there are differences later. So there is this frame header information, which important part is source MAC address for this frame, target MAC address and length and control sum for data, and then there is packet header for internet protocol as a data for this Ethernet frame, where you have source address and target address and source port number and target port number. And if it is TCP connection, there's also TCP data, where you count how much data were sent from client, how much data were sent from server, to ensure that everything is transmitted correctly, and then actual user data. So these repeaters and hubs, they are just electrical devices. Only thing they do is they may amplify signal for large networks, for long lines, but in general they just ensure that wave resistance for these networks is always correct, that there is no unneeded bounces forwards and backwards for these signals inside particular network. Then switches are more complicated devices and routers are even more complicated. So repeaters just and hubs, repeaters amplify signal and hubs just ensure that there is proper wave and electrical resistance inside this particular network. But for these repeaters and hubs, the most important limits are that they still cannot go beyond 2.5 kilometers, and also you cannot cover entire thing with just repeaters. And other thing is performance reasons. For example, Ethernet and Wi-Fi works that one device is talking, every other device is listening. And if you create large tree of just bridged or hub networks, that means that there will be too many listening devices, while one of these devices is just talking to another. And switches do not connect every computer to every other computer. They create virtual channels where one device is listening and another is talking in these separate channels. So that means depending on how many separate channels your switch has, you may have many concurrent talks and conversations going at the same time. Problem is that Ethernet is auto-configured network. How exactly these devices decides which particular Ethernet frame needs to be sent to which particular device. So they do so-called auto-discovery. And auto-discovery works in such way that if some device, and this device always knows what is its MAC address, sends to some other device to its MAC address. Then, if this switch do not know to which particular cable this MAC address belongs, it sends duplicates to this Ethernet frame to all connected devices. And when only this device answers, because that Ethernet frame was intended for that device, this switch remembers that MAC address at the end of this particular line is following. And when this device sends some new frame to the same MAC address again, it switch do not create copies of frames to all possible connections. It resends this Ethernet frame only to this intended device. So that means initially switches work like hubs. Only difference is that this frame is written into buffer and then resend from the buffer again. But when this device lands where particular MAC address is connected, then it uses these virtual channels to send Ethernet frames from device to device according to its knowledge. So, other problem is that you may accidentally create loops inside your networks. And when I worked in Exigen, that was approximately 15 years ago, switches were not so smart, and they didn't detect loops inside the network. And then what may happen inside this loop is that these Ethernet frames are resent in forever, because what this switch receives is sent to that switch and then it resends again. And one day we got network problem, so first our network in office becomes slower and slower and slower, and then it actually halted working. And when we checked what happens with network administrators, with some debugging, we saw that actually this network is very busy, but it is sending many Ethernet frames again and again, so no new frames could be resent, because Ethernet works in a way that if one is talking, everybody else in this channel is listening. And so what was happening was that in one meeting, one of board managers, that was when Wi-Fi was not used, mostly because of security, and even now many of offices do not use Wi-Fi because of security reasons. So in each meeting room there was some Ethernet switch with some cables here where attendants could connect their laptops. And one of board managers did following, that one of these loops he reconnected back to the same switch. And nothing happened for some time, but after some few minutes everything was halted in entire office, and you can check it by yourself. Does your network at home still works if you create such loop in your switch or not? But in most of cases today, these switches do check for loops. They add some signature as a data to, so they send Ethernet frame, and inside this Ethernet frame there is some signature, like and then some data, and then they check that this particular Ethernet frame goes back to input of device with back again for some particular loop. And so if you create some cycles accidentally, then modern switches disconnect these cycles automatically by this auto discovery of sending internally some diagnostic data through these frames. And so that is pretty good thing, because otherwise you always had to ensure that you have tree-like structure, no loops inside your entire office network by yourself. And so I will not go into details how it does this, but so switches are communicating each other, sending some other Ethernet frames which they generate by themselves, and then they vote which particular link is unneeded between them, and then they disconnect such particular link which is not needed for particular case. And if something breaks here, then they may try to reconnect again, because they see that there is some particular device which is not reachable anymore. So that's about switches, but about this loop, it was not easy. This meeting, I think, started at 10 o'clock, and we got actually network working in this office only in afternoon, sometime after lunch, I do not know, at 12 o'clock, 1 o'clock p.m. So outage was approximately a few hours. And so what is good about switches is that if you use modern switches, they can configure everything automatically, so your Ethernet network is almost always working. They also decides what is maximum speed for your particular connection, 100 megabits per second, gigabit per second, or maybe more, or maybe less. And so that is good thing. What is not so good is that still internet is not built only from sending Ethernet frames. You also need to assign these IP addresses globally unique if you do not count network address translation to make entire internet working. And so here routers come in. So routers are also switches in most of cases, but besides just handling this connection about Ethernet connections, routers also look inside data of these Ethernet frames and check what is source address and target address regarding to IP addressing system. And here problem is much more complicated, because entire internet is much more complicated than just few Ethernet connections with Ethernet network. And here different kind of routing protocols come in, and you may create this routing automatically or manually. And there are two different kind of routers. If somewhere here is internet, there are some of routers which are called on the edge of the internet. And edge routers are your home office routers, etc., where only few other computers are connected. So edge routers are almost always configured dynamically, because all they do is they send everything to the gateway. And gateway is this next router which somehow connects everything to entire internet. And so somewhere here is Microsoft, somewhere here is Google, and somewhere here is Amazon, and somewhere here is Facebook. And with that I have counted almost 3/3 at least of entire internet. But then there are these routers which are inside the network, which are not at the edge. So there are some routers which are connected to the other routers And these are these routers which create this backbone of the internet. And these may be configured automatically, but much more manual labor is needed, because here, for example, if you have such kind of connection and you send some data from this edge router, you may send data to the Google somehow from this route and also somehow from that route. And it would be very useful if actually both routes are possible, maybe with only some preferences, because if something is happening here, in one of cases this is out, then you can still reach Google through the different route. And so for such routers which are inside the internet, which are connected to the other routers, these are more complicated, and they are configured both manually and dynamically. Usually what is happening is that, particularly for example in Facebook, they have some of these routers. What strange color I was using. And these routers are usually called autonomous systems, AS. And AS are usually belonging to large IT companies, other large companies, government institutions, etc. So these are routers which are connected to other routers, probably with redundant connections. Difference is that in Ethernet you avoid redundancy, and if something breaks, you reuse redundant cables dynamically. But for routers, they are always redundant, but then you need to decide how exactly it should be routed. And so it was approximately 2 weeks ago, entire Facebook was off the internet. And what we know from public resources is that they misconfigured the autonomous system, one of these routers, that there was no routes to any of these autonomous systems from the internet to the Facebook. And because that never happened before for them, they were quite unprepared, because everything which they were using, like different kind of tools and utilities, were built on assumption that they always will have connection to the internet, the domain name system always will work, that their internal resources always will work, etc. So then these can be these routers exchange with data dynamically, and most widely used protocols how these routers say about reachability are two protocols: RIP, older school routing information protocol, and BGP from border gateway protocol. So what do these autonomous system does? One of these routers in Facebook says that if you want to get IP address like this address, then everybody from the internet should send packets to this particular autonomous system, which is one of routers of Facebook. And of course they may even have several autonomous systems, but all of these systems were misconfigured. And particularly with Facebook, what happened is that they accidentally removed and they sent this border gateway protocol, not BGP, announcement that all previous routes are wrong, so this need to be deleted, and no new routes were created after that. And so every time you wanted to reach some IP address which belongs to these data centers in Facebook, you got something like no route to this particular IP address. And sometimes there may be some cases when it was done on purpose. For example, if you look around the world, somewhere here is Europe, and somewhere here is USA, or let's say somewhere here is China. So there are many connections connected to Europe, to USA, to the China. And when you send some data from Europe to China, usually what happens is that through these backbone routers, your packets are traveling through the shortest possible path from Europe to the USA, usually around the Atlantic Ocean. But China, a few years ago, announced from this BGP protocol that if you want to reach some servers in USA, your packets actually should go through these routers. And for several hours in one day, every time you actually wanted to communicate from Europe to USA, all packets were traveling through the data centers of the China. It is assumed that they create a dump of all this data in their servers for later analysis, and of course this error was caught and it was re-established, and then because of that additional checks were introduced. For example, that if you get suspicious announcements about BGP, for example, that there shouldn't be any announcements from routers in China saying that you should send data through their network instead of shortest possible path. But here again, problem is that if it will be very strict and actually something will happen with some cable here between Europe and USA, then sometimes it's actually good that these packets are traveling through not so optimal route. So, and therefore here is always some friction between security and authenticity during normal situations, and how to make it dynamic, that if something actually goes wrong, that additional routes are actually working. And so how these routers are working? First, of course, you try to not create infinite loops. In difference with Ethernet frames, because of that, in Internet Protocol packet inside this data, there's one important flag or number inside packet, or this time to leave. So it never will be retransmitted more than total amount of hops or retransmissions between networks from one place to another. That is good, but there still these packets may be traveling in infinite loops, like 40 times, 180 times, whatever this particular number is set. And also you need to get some robustness and redundancy if something goes wrong with this particular connection. And in most of cases, therefore, idea for these routers is that they try to create copy of this packet or retransmit it farther away from source, closer to the target. So, and here graph theory is very important, and everything is about directed acyclic graphs. So what is DAG? DAG is any graph you have. It may have as many redundancies as you need and want. But idea is, and here usually there are no many choices at the end or borders of the internet, because usually you have just one client, which is not many farms of clients like distributed servers for highest route, but only one here. So if you send to this first router, then this router sends to its gateway. So there is only one possible way, and here is also one possible way. But here are different ways. And what these routers check is, for example, how many hops are in between. For example, here, this router decides that this is preferred route to go for this packet from here to here, because there is no any hop in between. Then this router also checks where is no hops in between, probably here. This router checks somewhere here. But there are also suboptimal routes which also work. For example, backup route may be this one, backup route may be this one, backup route may be this one, and from here again, actually this should be another option because here is only one hop. So this route could work as well. And then you can analyze how many hops are here. It may go from here to here and here as well. Let's simply use this other color. Or maybe here and here and here. And what is important here is that for one particular decision to make this algorithm more robust, they actually do not check travel of this packet from very early beginning till to very late end. What they check is, did I receive this packet from here or here? That means they will not resend any packet back here, only except something, your stupid packet died here. They always will forward to any possible path, probably to the shortest path away from the source. Something like what bureaucrats do. For example, if you receive something, just throw it farther away with as many possibilities as you have. And so that means that even though these routes may be very different, what is very important is that what is not allowed is, except error messages, to send this packet back where it came. And for example, if some packet comes here and it sees that it was received from here, it may be suboptimally sent somewhere here, and then it may be suboptimally sent somewhere here, but it was received here, it will definitely not be resent here. Then this packet will be tried to football or whatever you call it to retransmit here. So what these routers actually check is, they check was this packet actually received from this edge or this end, then it probably will not be used. And then, again, similarly to switches, they send their internal internet packets as well, just to check what connectivity is and to count how many hops do you have for particular order of this flow of packets from one place to another. So that's about routers. And so in such way, if there are no some funny accidents and malicious activities, in most of cases it works pretty well. But there are still different kind of struggles how to filter out these malicious activities, like Chinese government announces for some time that all the traffic should go through their particular routers. So that's about general routing. Now a little bit about physical things. In most of cases, for local networks, you use wired networks, mostly because they are physically easier to create and handle. For optical networks, precision is much bigger, and because of that, they tend to be more expensive. But a good thing about optical fibers is that they do not induce electricity. For example, if we have magnetic storms on Earth, then electrical networks may be affected, but optical networks are not affected. And also what is good about optical networks is that they are much easier to filter out particular bandwidth to send more data through the same cable. If you know something about Nyquist theorem, it says following, that if you look on spectrum axis, frequency here, and here is amplitude, and your basic frequency is somewhere here, but when you modulate according to Nyquist frequency, this frequency actually becomes wider, because if it's very sharp, it is precisely sinusoidal signal. Every time you modulate it a little bit, this means actual frequency changes a little bit forward and backward. And you can send as many as data as up to half of your base rate. For example, if here you have 1 gigahertz of frequency, you can send up to 500 megabits per second as a data rate. And that you may assume that maximum bandwidth or maximum data you can send if your maximum frequency which you can reliably send through the cable is just 500 megabits. But it's not the case, because you can create a little bit different amplitude here, which do not overlap too much. And this means that here you say, let's say, 800 megahertz, so you can send 400 megabits as well. And then there may be another signal here with smaller bit rates and another signal with smaller bit rates. And that means if you can create very sharp distinctions between these different kind of wavelengths and you can filter them out very sharply, then actually you may send not 1/2 of data depending on maximum frequency what you can send, but actually 1 gigahertz squared. Why? And then divided by 2. Because if you could filter out very many separate frequencies here, you can send more and more and more data there. This means in general you can reach almost squared amount of maximum data throughput through particular bandwidth through the network. But for electrical cables you cannot make this distinction very sharp. It is approximately, let's say, 10% or maybe 5%, no less. So that means it is actually much lower than that, because they are overlapping and you cannot filter them out very precisely. But particularly for light, you can filter out different wavelengths of light very precisely, much more precisely than accelerated current. And therefore you use optical fiber networks around the world, because you can send quite a lot of data if you use different wavelengths through the same cable. So this is this frequency multiplexing, when you put different colors of light through the same cable and then you filter it out very precisely and send this data. And because of that, in most of cases, optical networks are used for global networking through the network. And then one problem is that if you have short distances for networks, you may use less precision cables where actually signal can travel through this channel in different modes. And different mode in general is, for example, how frequently this signal bounces back from side to side. For example, you have this optical cable, high reflection rate of glass here, low reflection rate of glass here, and that means it happens that there is internal reflection here, and if highest possible mode to internally reflect is this one here, but there also may be another mode twice as long, like this mode, and then another mode 3 times lower, like this, 4 times, etc. So these are different modes, and it's easier to create such cable, but problem is that all these modes has different speed of light, and that means when you send very sharp signal at this end, because of these different traveling modes, you get it little bit later for one mode, little bit earlier for one mode, little bit earlier for another mode, so you get it smooth, smashed out during the time. So and that also limits what is maximum speed rate because of this. But if you create this cable much thinner, then there is only one mode how this signal can go through it, this longest possible mode. So you put this signal in, and it in general goes in parallel to this internal channel of this glass. So this is single mode, but it is much thinner here, so much bigger precision should be made, and such cables are much more expensive. And even with that, usually you need to have repeaters after a few kilometers of these single mode fibers. And that's about this. And so differences here is that only difference between electricity and light is that this physical layer is different. In optical networks you send changed light with lasers through the cable. With electricity you send changed accelerated current through these cables. And then there are different kind of other networks, like ATM, which was initially introduced for bank cashing machines, automata, and then there are other things, but I will not go in more details there. Now about mobile networks. I already told you, and you should remember, that Wi-Fi in general principles is very similar to the Ethernet, but there are huge differences, because if you use cable network, it is very clean, not noisy, and decay of signal is very slow. But for Wi-Fi networks, it is much more noisier, and decay of signal is much bigger, because signal is not traveling through this channel of the cable, but it's traveling through the entire world. And that creates problem, because old school Wi-Fi worked in the absolutely the same way as Ethernet. So if some device listens to this channel, in particular frequency spectrum of Wi-Fi, and this channel seems empty, so nobody is sending anything, it sends some data and waits for acknowledgement. But problem is that in Wi-Fi network there may be happening that if computer C is sending something to computer B, this computer may not hear that computer A is also sending something to computer B. For example, this is your home router, and here are two computers connected to this router, and computer C do not see or do not hear send signal from A to B because of some obstacle, because it's too weak, it doesn't go directly from here to here. So it sends this signal, but B is actually busy, because both A and C are sending something to it, so it cannot distinguish, so data gets garbled, signal gets garbled, and so no data are transmitted. And therefore for newer Wi-Fi networks, what is actually happening is that before sending actual data, they send request to send and then try to receive confirmation to send. So, and then instead of sending actual data, C sends requests to sending and A sends request to sending, and B of course responds confirmation to send only to the A or only to the B, and that works pretty nice. Only problem is that it increases latency, because it means before actually sending data you have another round trip just to get confirmation that this particular device by sending data to that particular device. And that's problem, for example, for gamers and other applications where latency is important, because Wi-Fi networks are in general have at least twice as big latency as wired network, and in practical situations it's almost 10 times more than for wired networks. And then about cellular networks. So Wi-Fi networks work in around 2 GHz to 4 GHz, somewhere here. But there are other frequencies as well, and in these frequencies initially there were very different ones. For example, there is still radio around 100 kilohertz and other things. But what is happening is that in this consortium which talks about usage of Ethernet, more and more wider spectrum for data transmission is given to data transmission. So initially there was very specialized bands, for example to send radio, to send television signals, to send something else. But now what is happening is, because data transmission is so universal, that if it's possible, more and more spectrum is eaten up from all other older technologies, and more spectrum is given just to data transmission. And here comes this cellular network or mobile phones, which have different kind of generations. Zero generation was just radio telephones with analog transmission. Third generation was analog with cells, which means one particular phone is working and talking only to one particular tower. And starting with 2G, it was actually digitally managed, but till to 3G it was still circuit-based transmission. I hope you remember. So circuit-based transmission means that before you send your call data, there should be established virtual channel how you can send your voice data from one telephone to another. But starting with 4G, which is de facto standard here in Latvia, and 5G, it is actually packet-based like normal internet. So when you send your voice data with 4G, there is no virtual circuit created for these data packets sent from phone to phone. What is actually happening, these cellular networks work like internet. These data are split in small chunks, and all these data are sent just closer to direction of opposite end of your conversation. And then, of course, technologies has changed how exactly you did this multiplexation or parallel concurrent sending of data. Initially, it was like time division. This means all devices used the same frequency to send data, but they listened to the ether, and then when the data came, one particular device could send in this particular frame. So it worked in such way still to 3G, But of course, it requires much more management, and if this particular frame is not used, then this time is just lost, and total speed of transmission is also lost. And starting with 4G and 5G, they introduced another interesting idea, is that many phones share the same frequency and the same time. So when I talked about possibilities how to share particular channel, there was two ideas. First, division by time. So here is amplitude, and different senders send something in different time, but that means that frequency is shared, the same frequency. Or they can use different frequency, lower frequency, higher frequency, more higher, and the time is always shared. And it looks like there's only two possibilities: either do it in the same frequency in different time, or during the same time but on different frequencies. But starting with 4G and definitely 5G, they introduce a different thing, that both the same time and the same frequency is used, but these then are mixed up. This means that a wider scope of frequency is used and wider time is used as well. So how can you filter them up? And you filter them out with additional modulation of pseudo-random code, which only sender and receiver knows. And this particular pseudo-random code is what your SIM card in mobile phone knows, and your central. So that means that if you look on particular time, on particular window of frequency, you see that many phones are using the same range of frequencies during the same time, but only difference is that each particular phone has different additional modulation for this signal, for this particular pseudo-random code. And you can use special devices called, I don't remember, collimators or whatever, to filter out, and this is actually the most efficient way how you can make faster data transmission, because you don't need to manage neither time for this who speaks next, and you also can use wider frequency spectrum. And as wider frequency spectrum you use, you should remember, this means you can send more data. If you use very sharp signal with not modulated frequency, you can send only up to half of amount of data depending to the frequency. But if you use wider and wider frequency spectrum, you can put more and more data there. And so this is called code division multiple access. So initially it was either frequency division, so different phones hopped around to different frequencies to use, and this is, for example, what your home routers does. Home routers decides either manually or by itself which is the least crowded particular frequency in home, and then use it. And then inside this frequency they use this time division, then one talks, everybody else is listening. But for mobile phones it is currently this code division, that each phone knows what its unique pseudo-random code is, and to filter out from this entire noise, you apply this filter to this code and you get this signal out. So, and then with 2G you still had this circuit switching in phones, like for old school fixed lines of fixed phones, but starting with 3G, it is actually also packet switched network, so there is no established virtual circuit between sender and receiver. They are just a bunch of packets hopping from one transmitter to the another. And then for each particular generation of these cellular networks, this bandwidth which is used is always becomes a little bit larger and larger because it's the most usable way to use this. And so for starting with 4G, which is de facto standard in Latvia and modern countries, so it is optimized for internet protocol traffic, and so everything is just data packets traveling from phone to phone or phone to internet. So there is not much of difference. Do you send voice through these packets or SMS or some data connected to the internet? But starting with 5th generation of mobile networks, they actually reached some problem, physical problem. And these who do not know physics, they are usually big techno-optimists regarding to cost of traveling, cost of energy, and cost of telecommunications. But physical laws always beats up optimism and political laws. And when you use wider and wider spectrum of light or electromagnetic waves to send data, problem is that if it's frequency, depending on what particular frequency this light has, it interacts with matter in very different ways. So something here with low frequencies behaves much differently than something here with high differences, high frequencies. And what are these differences? You should know from secondary school physics that light is both either waves or particles, and for long waves, waviness of light is more important, and for short waves, particles become, or particle side of light becomes more important. And for example, if you have very long waves and very small obstacles here, like tree or single atom or whatever, then long waves or radio waves in this case just go around these obstacles like waves go around some obstacles on surface of water. So they do not interact much, they just go around it and that's it. If this wavelength is very short, like it is ultraviolet light, actually gamma rays and Röntgen rays, for example, etc., then these are so short that this particle part of them are more important, but they usually just go through these atoms of some matter without any interaction at all. But if there is somewhere in between that sizes are length of wave is similar to size of these obstacles and how many these obstacles you have, then light start interacting. So it can interact in two different ways. It can bounce back, then you may have surfaces which reflects light, like mirror, or it may do non-elastic collision, so some of this wave or light matter just goes into matter, excites some electron in this atom, and then it heats it up, and then it's absorbed. And particularly for 5G is that there are some of these frequencies in light which starts bouncing back from walls and which are absorbed. So this wavelength is not so high as for Röntgen and gamma rays, which you use for röntgenoscopy in medicine, but it's also not so long that it goes just around these obstacles like actual waves, and therefore 5G is much more complicated. And it uses 4 different levels of these cells, so there is not just only phones and cells, but there are phone, femtocells, picocells, microcells and macrocells. So it's actually 4-layered network. And here this highest frequency is used, where actually this light bounces around, and either bounces around walls or it is absorbed by walls. So it actually is invisible light, like infrared light. So you can use it only somewhere in office where you can clearly see these devices. Then there is picocell, where it do not bounce around walls and goes through the walls a little bit better. So then you can use it for tens of meters. And then these microcells and metrocells, they are approximately the same as for up to 4G networks. So it can go through the walls and go around smaller obstacles. So then it is for larger distances. And but here, because frequency is the highest, here also possible theoretical speed is the highest, because of this Nyquist theorem that you can send up to half of speed of data through particular channel depending on its frequency. So, and because of that, 5G is much more complicated, because here with higher frequencies you have this problem that these frequencies are actually interacting with matter much more than these lower frequencies. And then other thing is, for example, about GPS. And in old times you had to count time precisely and look on North Star to know your place. And I think rudiments from this is still in our education. Because of that we are still learning quite a lot of stereometry and trigonometry, which was some of these navigation things. But nowadays we are using GPS system, and in GPS system they are using thing actually called trilateration. Triangulation means you can check your position depending on angles when you check where something is located. But in GPS, what actually is happening is that there are these satellites with very well-known orbits, and they send precise time to the world, and this time is with precision with picoseconds or nanoseconds. And when you receive time from different sources, then you can calculate where you are between these two satellites, because for example, if here you reach this time signal a little bit earlier than here, then you know that you are a little bit closer to this satellite than to that satellite. And if you add third satellite, you know your position very well in one plane. If you add fourth satellite, you even know elevation. Of course, if they are not all on the same plane, and of course they are not on the same plane. And so what is problem about time? That time is actually quite complicated thing, because if you check time with precision of nanoseconds or picoseconds, then neither of astronomical objects is precise enough. And to check this time, you use atomic clocks, which has precision up to 10 in, I do not know, tens or 11s or whatever, and you check this time very precisely, and then you compare it with rotation of Earth, and you see that rotation of Earth sometimes is actually quicker, sometimes not so quick. It depends on how this core of Earth is moving around. And because some 40-50 years ago they didn't have so much precision about rotation of Earth, what actually happened is that what is considered 24 times 60 times 60 seconds in a day is actually a little bit shorter than actual average day on the Earth. And therefore this atomic time, which counts these very precise seconds, is gradually going ahead of our normal time. And then they introduce so-called leap seconds when this difference between atomic time and coordinated time is larger than half a second. And you see that in most of times you need to add this leap second after a few years, but you see that sometimes this this speed is not so big, sometimes it's bigger. And for last few years again, Earth is actually still rotating a little bit slower than considering the atomic time, but faster. And from this atomic time to our coordinated time from 1970s, there are 37 seconds difference. And particularly for GPS, they are using atomic time because it's much more precise than these things. And so what is problems? Problems are, again, that this signal about time can come not from shortest path but other passes, so you get some errors there. Also because of political reasons, there may be wrong maps like in China. So, and therefore, even though theoretical precision is up to centimeters for GPS, practical precision is approximately a few meters in some handheld devices like mobile phones. And I think that's it about networking and how they are used. Do you have any questions or comments on that? Now about your practical exercise, because before we go forward, I will try to explain where some problems may be regarding to your previous task. I'm still not sure where actual problem is. I can just explain a little bit more about archives. And here I have some test files, PNG file is such image, which is archived in two different ways, with extension .tar and extension .tgz, which also may be extension .tar.tgz. What does it mean? It means following. The tar is de facto standard for archives where you can put many files inside one single file. And it doesn't have any compression. It just describes where metadata about one file starts, how long it is, date about this file, other file, etc. And when you create such archive, you can put many files in it, but if you need to decompress it, then you just use tar utility, which comes from tape archive. So initially this utility was used to put data on tapes. But at least in my environment, you can open it and extract. Very easily. But type of it is different. And if I look, for example, it says that format for is POSIX tar archive, but if I check how I call it, it's wrong, it should be renamed either TGZ or so. It may be named either in such way or in such way, and so this tar.tar.gz may also be a tar file which is compressed using gzip utility, and when you extract it you can do it in following way. You can say tar xzf AA tar gz, which means extract file and use gz utility also to decompress it. Or you can use just tar xf extract file, and then it creates, I will show you. So if I just extract it, it creates what kind of file? I don't know, but with some utilities you may do not everything at once, but first decompress it using gz utility or gzip, and then you need, but as far as I can tell, if you have not misconfigured anything, then it should work automatically. And I also check it, for example, for this file which I downloaded. So it is gzip compressed data, and I can open it. Oh, maybe something is wrong with this gzip archive. Oh, no, that is about this particular file. That's interesting. So now at least we got error. And if it's not tar. Something is broken for this particular file. Okay, at least now I know what is problem. Let's double check. Okay, then that is homework for me. So, and now about next task about networking. So, if you use this virtual machine or physical machine, which is Linux based, and in this case also Debian based, and which uses apt or Debian format for package management, you can install this Wireshark utility in command line in following way. And if you do it first time, I think I have not installed here in this virtual machine. Also already installed. When you install it first time, it asks, do you want your current user to open this Wireshark without root permissions or not? You may say yes or no, whatever. For me it's easier to say no, and I always do following. I escalate my privileges to super user with sudo su, and then I call it and add ampersand, which means run it as a background process. It's not required, but if it's not, will be background process when you close this terminal. This child process of Wireshark will also be closed. And then you prepare your terminal. Don't do anything yet. Check where you need to capture, and you should know what is your active network card. So this is my active network card. I start capturing it, and then I enter it. And stop it and save file. Save as. What was my number? This extension will be added automatically, I don't know. Yeah. And then check that there is no other noise here. And you should analyze what is happening here. What we see is at first DNS request was issued to the DNS server, which is in this case local router to this virtual machine, to know what is IP address for Odo.lv. Then it was responded. Then why these are shown UDP, not ECMP packets, I do not know exactly, but I will leave it up to you. And so here I think that maybe it is described as a UDP instead of ECMP packet, because here when we look on data, what it says, some data sent, but this is target address, and quite other things are happening here. So, and you need to analyze it, and then you need to describe what exactly you saw there, and there shouldn't be too much of noise about other activities, but there may be something, and you need to describe what is actually happening there. And that is first task. And second task is to know how to create remote connection to remote servers. And if you use graphical connection, then de facto standard is utility called TeamViewer. And how does it work? It works in the following way, that if you have many independent devices, you install TeamViewer client, and when you run it, this TeamViewer client creates connection to the big browser, which is this TeamViewer servers. This client creates this client, creates this client, creates, and then when you want to actually connect to this device, you create another connection through the big browser and you connect to this device and you can manage it remotely. So this is very convenient. I have used it for my work. What is not so good is that all the data are sent through the big browser. And much more, and if something happens with big browser, like with Facebook 2 weeks ago, then nothing will work for you. But of course here are many independent routers between your computer and big browser computer, and if you could create more local connection with internet, something like this, then of course it would be much more robust solution. And such local connection for text is SSH, for Unix-like system like MacOS, Linux, etc. And for graphical it is VNC protocol from Virtual Network Computing. VNC initially was developed for mainframe computers, where you had mainframe, which was actual computer, and then instead of text terminals, like for weaker computers, you had graphical terminals. And only difference between text terminal and graphic terminal is that instead of sending text here, graphic was sent back from mainframe to this terminal, but it still was not real computer. It has some processor, some memory, etc. only to handle requests from mouse and keyboard to the real computer and to receive and handle graphic back on this graphical display. But you can use the same protocol also to connect two different computers. And later Microsoft introduced another protocol called RDP, Remote Desktop Protocol, which does the same particularly for Microsoft Windows based computers. And I think that during this course, to learn about technologies, you should also know how can you create remote connections without help of big browser. And if you use Unix-like system, then creating remote connection with text interface is very easy. It's built-in feature. You run SSH application, which is client for secure shell, and here you say which user at which server, and password is the same as you showed it in previous session, RPC702, and we are in, and when we check here we see that now this is user RTSS at tools server, not at this local. And here, to prove that you connected successfully to this server, proof of work is done with specific application, which is packaged into Java archive, and we need to add additional information to it, and it creates encrypted session together with this name, and so you need to copy it and save it as a sad exercise sad file, I think. Then this remote server also allows you to create graphical sessions, not only text sessions. And I think that by default on these computers, this client which you may use to connect to remote server is not installed by default. So you install it, but maybe it's installed, I don't remember. And then you run it. And you can customize it as you like, but in general you can use VNC protocol for this data. Say server is tools LV, port number 5901. And again the same password, RTC702. And then you can improve transmission quality in additional settings. And again, you need to run this. And there are strange settings for this session. Current directory is not home directory of the user, but a root folder. So you can be very ceremonial and say something like this, but cd without parameters also changes your current folder to your home folder. Yeah. I will add notes. So in this terminal, adding cd will help a lot before you execute this Java application. And then you run it and you will get a little bit different encryption of your session. And that I think is like force file in this exercise. And this server actually is allows you to use remote desktop protocol as well. Then it is standardized, you don't need to put anything here. Then accept this certificate. Here you need to change port number to 5901. And here RDP protocol is worse than VNC. For example, here it doesn't work with Latvian modern keyboard layout. I still need to use English QWERTY keyboard layout. So be sure that you are using standard American QWERTY, English QWERTY keyboard to connect to it. And then everything else is similar, but difference is that now these data for remote desktop are sent using RDP protocol, not VNC protocol. And now we still have a little bit of time. So if you are still using Microsoft Windows, which is not the best operating system except for Microsoft Office, then of course your life is a little bit harder. These others. So you'll need to install Wireshark compiled for Microsoft Windows. You also need to download or there's a download or install this PuTTY utility, which is already done for me on this virtual machine. And also free RDP utility as an open source free application. In older Microsoft Windows, they had built-in remote desktop client built-in and packaged inside Microsoft Windows already. But for some reason, for more recent Microsoft Windows versions, they do not provide it. I think because they like that you are using some solutions through the big browser. So they do not like such distributed solutions when you can do whatever you need without reliance on big browser, and I think that's why they do not include it in Windows by default anymore. Will it work in such way? So here this installer provides quite a lot of different choices, but because I have never used any choice besides this allow to run it without user privilege or not on Linux, I don't know. Mostly I use default options. And here it is just archive, you need to extract. How do I extract it? Okay, in such way. So then again you need to prepare your command line window. I have too many open windows, but I can close this one. I think I can start recording on this interface. And I will not be surprised if here I will see much more different garbage. What Microsoft Windows is sending to different big browsers here. Actually here you can add also filters while you are recording, but particularly for traceroute application, of course, you are interested about all intermediate passes here. So filtering for one particular address when you just communicate with one single server is easier, but filtering out for these particular addresses which you don't even know in advance is quite hard. So I got tired of waiting, so you wait till to the end and you save it. Again, here too many different options, I think. Okay, let's use forced extension for it to know that I need this format. And to check, of course, you may try to open this file. Where did I save it? Here. Looks okay to me. And of course, for Microsoft Windows users, you'll need to explain much more what is actually happening with your Windows computer. So then about this second task, if you have installed PuTTY already, you run it, and here write tools, Ctrl+V, open, login as RTSS, RTC502, and got what is proper way to go to my home folder? This is quite insane. And then to run this RDP client, you'll need to run it from command line because you need to pass settings to it. Check that this utility is extracted here, and here it is. Then you can run it, and of course I think I copied everything here. So you run this utility and you say connect to this particular server. Again, for RDP protocol, you may go into settings. It is just standard QWERTY keyboard layout by default. If you use non-standard, then be careful. And I pressed some wrong keys here. And you got another encrypted data. I copy. Then you either rewrite it or you may store it like in temporary folder. Where is larger than and then you can use like Midnight Commander to get this file. Otherwise it is a little bit too large to retype everything correctly. And by the way, other utility you can use is use VNC protocol. Maybe it's actually easier. I will update this guide. Because I thought that particularly for Windows using RDP protocol maybe is easier. And if you have built-in RDP client in some older version of Windows, maybe this works well as well. So if you use utility for VNC protocol, then one of utilities you may use as a free open source is Tight VNC. I don't don't need tight VNC. And this actually may be used also, which you can use for remote desktop connection to this computer. I'm not sure that I installed proper one. Okay, if you will have some issues, if you want to use it, then we can again go back to it in next session. So on here we need to say port number. Let's check, does copy paste works from this to that? Also doesn't work. So that's again one option where Microsoft Windows is much worse system than Linux based, because from neither of these remote session clients you can actually use copy paste. So but it is doable, only you need to suffer a little bit more. And then review your prepared files. Not these dots. And upload them. I'm not sure. Double check if you are using Windows that, for example, here you see proper extensions for these files. So here, for example, so these are properly ready to upload, and that's it. Any questions, comments on that?